with nomenclature. Let's talk about binary molecular compounds of two nonmetals. Nonmetals are, of course, these elements in the upper right portion of the periodic table, including all the ones to the right of the metalloids colored in lines here. Turns out that these are going to be the covalent compounds as well, meaning they will have covalent bonds. They will form molecules with those covalent bonds, and there are many possible combinations. So unlike ionic compounds, where there's just one set of ions for each charged ion compound that it forms, and they combine to cancel the charges out, there are many options, and so we will need number prefixes for these. And so looking at some of these examples, let's go through what the number prefixes are. Number prefix for half is going to be hemi. Then mono, di, tri, tetra, and penta. And these little dashes mean these are prefixes. This part of the word attaches to the rest of the word. Hexa for 6, hepta, octa. Then nona and deca. And of course the number system goes and does all the numbers, but these are the limited set of numbers that you have to memorize for this class. Let's go ahead and start naming binary molecular compounds now. This first one is going to be nitrogen monoxide. And two things about this. First off, and I'll put these rules up here, if the first element only has one, omit mono. Omit mono, so nitrogen monoxide. Otherwise, the first element is just the name of the element, and the second element has the IDE ending as if it were in a monatomic ion. So oxide would be O2 minus, and so oxide is the name of the second one. Chloride, even though it's -1, all the IDE endings are in effect for the second element. Okay, then the other thing is, typically when you have a mono and an oxide, so OO, which would be for mono and oxide, contracts to just O. And the other one you'll see is AO, as if we had pentaoxide. So both of these contract to just O. So that's why there's only one O here. Though, and this is proper, though oftentimes you will be able to look them up with the OO or AO, and therefore, when you do the homework, quizzes, and exams, I will accept these answers. But know that monoxide is better than monooxide. And pronunciation here is a good key. If it's tough to pronounce, it's probably not the correct way to do it, though it is acceptable. Then here, this would be nitrogen dioxide. Dinitrogen monoxide. And so you can see that if you know these prefixes, you can recognize that they're binary. Bi means two. Molecular, meaning it's a molecular compound made of two elements. You can put them together in this way. But you do have to memorize your number prefixes. Dinitrogen for this last one over here. Tetroxide, like so. sulfur hexafluoride. One thing to be aware of, spelling does count when we do nomenclature on quizzes and exams and homework. So please be careful. Fluoride has UO. It is not fluoride. Flour is what we use to bake bread. Fluoride is what we use to do chemistry. Disulfur decafluoride. Like so. More practice. We'll leave these for companion problems. And as far as nomenclature goes, we're going to ask you to be able to identify several different types of compounds, be able to identify the following functional groups, and that's a word for parts of molecules. Anytime you see something with the ANE ending, it will have the formula CnH2n plus 2. For example, C3H8 follows this formula, and it is propane. CH4, methane. And the ANE ending signifies that all carbon-carbon bonds are single bonds. All carbon-carbon bonds are single bonds, and that means that in propane, we have 3 carbons, and I'm going to draw the Lewis structure, though we're not there yet in class. In hindsight, and when you look at your notes later, you'll be able to perhaps understand this a little better. But it does have all carbon-carbon bonds as single bonds. Second functional group it'll be useful to know are the alcohols. Alcohols include the hydroxyl group, an alcohol group in ethanol. Ethanol being the alcohol in beer, wine, and other alcoholic beverages. Eth will mean 2 carbons, OH. Now, I wanted to draw a distinction here between the OH group, which is called the hydroxyl group, and the hydroxide group. It's very important to be able to tell these two apart. The hydroxide group is an ion. It exists by itself. It forms formula units and ionic compounds, but only because of the attraction to positive ions. Hydroxyl group that is in alcohols is covalently bonded to another part of the molecule. And you can see that hydroxyl groups show up when all of the nonmetals are there as well. Metal, sodium, going to be a hydroxide group. And one of the take-home messages for the whole class is when we talk about intermolecular forces much later in the course, is going to be being able to tell hydroxide and ionic compounds from alcohols in covalent compounds. Here we see again our organic acid, carboxylic acid, that's a new name, group. It's called COOH group, and it is a weak acid. And a very common weak acid that has this is acetic acid. And acetic acid is the acid in vinegar. Ooh. Now let's start over again. Here is our COOH group, how we always draw it, and we'll talk more about why it's an acid later. Just start to think about the fact that, and memorize that it is an acid. And we said this is the acid in amino acid groups. True. Now let's talk about the amino group in amino acids. It is a weak base. It is an amine group. The smallest amine is ammonia, where the dash part where it's connected to some other portion of the molecule, the other portion of the molecule is just an H. Sorry. There we go. There's our NH2 group attached to something with carbon on it. This, the name for this is methylamine. And amine groups, when you have an amine group and an acid group in the same compound, that's when you get an amino acid. We'll talk more about those later in the course, and you'll definitely talk about them in biology. Cycloalkanes have a ring structure and a general formula of CnH2n. This is a 6-member ring. Here is a 6-member ring as well. We will fill in each of these carbons until it has 4 bonds. And we will see that there are C6H12, so Cn to H to the 2n. Alkyl functional groups, these are going to be parts of molecules, and they're called methyl, ethyl, propyl, and butyl. And when I say parts of molecules, if we take, as an example, the following molecule, something with 8 carbons in it, and off of the sides, and off of another side, we have branches. Those are what are called alkyl functional groups. They're branches or parts of molecule off of what's considered the backbone. And then we'll fill in all of our hydrogens until each carbon has 4 bonds. And what I've added here, so here is our longest part of our molecule. This would be what's called an octane, because it has 8 carbons in a row, that's octa. All of them are connected by single bonds. And then off the sides of this, we have a methyl group and another methyl group. And so you want to be familiar with these. You'll start to see these names show up in all kinds of compounds as you look in your daily life. Now, we've talked about isomers once before. I want to do a specific example of isomers. This is going to be C5H12. For C5H12, we now know a couple things about this. First off, this is an alkane. Because it follows the formula CnH2n plus 2. We know this is not a ring structure because ring structures have CnH2n. Now, isomers are going to be molecules with the same formula but with different atom arrangements. Here's one isomer. Put all 5 carbons in a row. fill in the hydrogens until each of the carbons has 4 bonds. And lo and behold, you'll find there are 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. That's one isomer. And it's always the easiest isomer. When you make other isomers, what you're going to want to do is you're going to want to take the carbon off of the end and stick it back in the middle to form one of those methyl branches. And then again, if you fill in all the carbons with hydrogens until each of the carbons has 4 bonds, we can show 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a second isomer. And it gets tricky because if you try and do, and I'll do this in this one, even though it looks different, this is really 4 carbons in a row with a branch starting off of the second carbon, 4 carbons in a row with a branch starting off of the second carbon. And so it gets a little tricky, and it helps to have modeling kits. And when you take an online class, you do not have a modeling kit handy. So this will not be a huge emphasis on being able to construct isomers. But you should know what they are, and you should have a general idea of how to construct them. It turns out that the only other isomer here has a carbon pattern in which there are 2 methyl groups off of the center carbon in a 3-carbon chain. One general trend for doing isomers, if you start with the longest chain, move from 5 carbons to 4 carbons, or this could be 4 carbons as well, either way it works, to 3 carbons. And I'll go ahead and fill in the hydrogens here. Why? Because it's hard for me to see it without its hydrogens. It just doesn't look right. And lo and behold, we get 12 hydrogens.